Welcome. Chromatography is a technique used to separate and identify different substances in a mixture. It works because different substances move at different speeds through a stationary phase and a mobile phase. Role and purpose of chromatography in chemical analysis, principles of separation, distribution between two phases, stationary and mobile phases explained with examples, overview of chromatographic techniques. Chromatography is a core analytical technique in A-level chemistry used to separate, identify, and sometimes quantify the components of a mixture. Its importance lies in the fact that many chemical samples, particularly organic compounds, are not pure and cannot be analyzed effectively without first being separated. Chromatography allows chemists to exploit differences in physical and chemical properties such as solubility, polarity, and intermolecular forces. It introduces more quantitative analysis, such as the use of RF values and retention times. In real-world chemistry, chromatography is essential in pharmaceuticals, forensic science, environmental monitoring, and food testing. For example, drug purity testing routinely uses chromatography to confirm that an active ingredient is present and that harmful impurities are absent. The fundamental principle behind all chromatographic techniques is the distribution of substances between two phases, a stationary phase and a mobile phase. When a mixture is introduced into a chromatographic system, each component repeatedly partitions between these two phases. The extent to which a substance spends time in each phase depends on its chemical properties, particularly polarity and the strength of intermolecular forces. Components that are more soluble in, or have a greater affinity for, the mobile phase will move more quickly through the system. In contrast, substances that interact more strongly with the stationary phase will move more slowly. This difference in movement results in separation over time or distance. In chromatography, the stationary phase is the material that remains fixed in place, while the mobile phase is the fluid that moves through or across it. The stationary phase can be a solid, such as silica or alumina, or a liquid supported on a solid surface. The mobile phase can be a liquid solvent or an inert gas, depending on the technique used. In thin-layer chromatography, the stationary phase is a thin coating of silica gel on a plate, and the mobile phase is a suitable solvent such as ethanol or a hydrocarbon. In column chromatography, the stationary phase is packed into a vertical column, and the mobile phase flows downward under gravity or pressure. Gas chromatography differs in that the mobile phase is an inert gas like helium, while the stationary phase is a microscopic liquid film inside a coiled column. Thin-layer chromatography, TLC, is the most prominent and is closely linked to required practical work. It is used mainly for identification and comparison of substances using RF values. Column chromatography is included to demonstrate preparative separation, where components are collected as they elute from the column. Gas chromatography, GC, sometimes referred to as gas-liquid chromatography, is used to separate volatile compounds and introduces the idea of retention time rather than distance traveled. Finally, gas chromatography mass spectrometry, GCMS, is presented as a powerful combined technique that allows both separation and structural identification. Thin-layer chromatography apparatus and setup, calculation and meaning of RF values, factors affecting RF values and separation quality, using TLC for identification and purity analysis. Thin-layer chromatography is a widely used analytical technique in A-level chemistry because it is simple, visual, and effective for separating small samples. The apparatus consists of a TLC plate coated with a thin layer of silica or alumina, a developing solvent, and a sealed container to allow the solvent to rise by capillary action. A pencil line is drawn near the bottom of the plate to mark the origin, ensuring that it does not dissolve in the solvent. Small, concentrated spots of the sample are applied to this line using a capillary tube. The plate is then placed in the solvent, with the solvent level below the spots to prevent dissolution into the solvent reservoir. As the solvent moves up the plate, components of the mixture separate based on their interactions with the stationary and mobile phases. After development, the solvent front is marked immediately to allow accurate measurement. Many organic compounds are colorless, so visualization techniques such as UV light or iodine are used. The retention factor, or RF value, is a dimensionless number used in thin-layer chromatography to help identify substances. It is calculated using the equation RF equals distance moved by the substance divided by distance moved by the solvent front, with both distances measured from the origin line. Because it is a ratio, the RF value has no units and always lies between 0 and 1. Each compound has a characteristic RF value under a specific set of conditions, including the solvent, stationary phase, and temperature. This means RF values can only be compared if the chromatography has been carried out under identical conditions. In practice, unknown substances are identified by comparing their RF values with those of known standards on the same plate. A higher RF value indicates that the substance is more soluble in the mobile phase or less strongly attracted to the stationary phase. Several experimental factors influence RF values and the quality of separation achieved in thin-layer chromatography. One of the most important is the choice of solvent, or mobile phase. A more polar solvent generally increases RF values for polar compounds by competing more effectively with the stationary phase. The nature of the stationary phase also matters. Silica and alumina differ slightly in polarity and surface properties. Temperature can affect solvent evaporation and molecular motion, indirectly influencing results. The amount of sample applied is another critical factor, as overloading the plate can cause spots to spread or overlap, reducing resolution. The size and uniformity of the stationary phase particles also affect separation efficiency, though this is more relevant to industrial contexts. Thin-layer chromatography is commonly used to identify substances and assess their purity. For identification, an unknown sample is run alongside known reference compounds under identical conditions. If the unknown produces a spot with the same RF value as a reference, it is likely to be the same substance. For purity analysis, a pure substance should produce a single spot, while an impure sample produces multiple spots. This technique is widely used in organic synthesis to monitor reaction progress, checking whether reactants have been consumed and products formed. Principles and uses of column chromatography, gas chromatography, conditions and suitability, retention time and interpretation of gas chromatograms, gas chromatography, mass spectrometry, GCMS. Column chromatography is a technique used primarily for separating and collecting components of a mixture, rather than simply identifying them. The stationary phase, often silica or alumina, is packed into a vertical column, and the mixture is added at the top. A suitable solvent then flows through the column, carrying the components at different rates. Substances that interact weakly with the stationary phase move faster and elute first, while those with stronger interactions elute later. Gas chromatography is a powerful analytical technique used to separate volatile compounds. In this method, the mobile phase is an inert carrier gas such as helium or nitrogen, while the stationary phase is a thin liquid film coated onto the inside of a long, coiled column. Samples must be vaporized before entering the column, which is why GC is only suitable for substances with relatively low boiling points or those that can be vaporized without decomposition. Separation occurs because different compounds spend different amounts of time dissolved in the stationary phase versus being carried by the gas. In gas chromatography, components are identified using retention time rather than distance traveled. Retention time is defined as the time taken for a compound to pass through the column from injection to detection. Each substance has a characteristic retention time under fixed conditions, allowing identification by comparison with known standards. A gas chromatogram displays detector response against time, producing peaks for each component. The position of a peak indicates retention time, while the area under the peak is proportional to the amount of substance present. Gas chromatography mass spectrometry combines two analytical techniques to provide both separation and identification of compounds. First, the mixture is separated by gas chromatography, producing individual components at different retention times. Each component then enters the mass spectrometer, where it is ionized and fragmented. The resulting mass spectrum provides information about the molecular mass and structure of the compound. Required practical skills linked to chromatography, analysis and evaluation of chromatography data, common misconceptions and how to avoid them, exam strategy and summary of key takeaways. Chromatography is closely linked to required practical skills in A-level chemistry. Students must demonstrate competence in setting up experiments, making accurate measurements, and recording results clearly. This includes safe handling of solvents, correct use of capillary tubes, and proper disposal of chemical waste. Students are also expected to mark solvent fronts promptly and measure distances accurately to calculate RF values. Analyzing chromatography data involves more than simple calculation. It requires interpretation and evaluation. Students may be asked to draw conclusions about identity, purity, or composition based on RF values or chromatograms. They must also consider limitations, such as overlapping spots or peaks, and suggest improvements. For example, using a different solvent or repeating the experiment under controlled conditions may improve reliability. Students studying chromatography often encounter recurring misconceptions that can limit exam performance. One common error is assuming that RF values are fixed constants, rather than condition-dependent ratios. Another is confusing retention time with peak height or area in gas chromatography. Some students also incorrectly describe separation as being due to molecular mass rather than intermolecular interactions and solubility. Chromatography separates mixtures by differences in movement between a stationary and mobile phase. A-level expects you to understand the principles, calculations, and applications of chromatography techniques. Thank you for watching.